Cal's there. Okay. All right, Cal. We're having trouble with the, oops, maybe we might not get it. So Econ 431. See you, Cal. There you are.
Sweet.
Econ 431. Literature. There it is. There it is. There it is. That's it. Let's get it up. Okay.
Okay, guys, you're in business.
Okay. Yeah.
Yeah, we can
I'm going
see.
to call her back when I go switch to the webcam to draw some figures. But anyway, so this is the second lecture, really the third lecture, of course, but first lecture, as you know, those of you who were there, was an overview. So Noah, what you missed in the very first lecture, which we actually had live, was I went over the course, and there's some things that you'll need to know. By the way, one thing I'll let you know that the others have heard is that homeworks, I'm probably the next class period I'm going to send you the first homework. You can cooperate on the homeworks, but you don't get to cooperate on the exams. So you're going to be getting your first homework, but it's not going out today. But you'll have a good deal of time to do the homeworks. Yeah, whoever can make themselves. I prefer to see people. Pretend we have a class, but I saw you before, Cal. You disappeared again. So I know Mason's got a problem. But anyway, we're welcoming Noah, who's hiding. I don't know, Noah, if you can make yourself visible or not. Maybe you have a problem. Maybe you want to hide. I'm not going to force people to be visible. There's Cal. He's showing himself.
Yeah, I just had to get my next book.
Okay, people have different issues. So probably next time I will send you the first homework, and I will give you lots of hints about things to do and what you need to be on top of and what you need to do and so on and so on. And again, of course, the homework problems are going to be more difficult than what you're going to get on the exams, because you'll have lots of time and you can cooperate and you can use your books and use everything under the sun to solve them. Whereas the final exams, it will be synchronous. All of the exams will be synchronous and like an in-class exam with a limited amount of time, all that kind of stuff, and no cooperation. For Noah, that's amazing. So I think you all got the message, hopefully, that supposedly the packets are in. I don't know who's still in town or not, and I suspect the bookstore is going to close by next week. So I do note, and this is always I noted at the very first day, that you have a question, Cal? You got your hand up.
Yeah. So what is it? Noah actually went to the bookstore today, and Evan did earlier, and they told Noah that they would not have the course pack printed out until next week.
No, well, I was told that they're there. They should be there. They were taking them over today, so I don't know if you go to if somehow they don't get them there.
Yeah.
No, they've been printed. They were ready to go. The people at the printing service just had not sent them over. So it was a question. It's a question. And I had a message from somebody saying, "Oh yeah, we took them over." So, but I wasn't. It depended on what time you went. If somehow they aren't available, I mean, the readings. You can just get all of those through JSTOR, through the library individually, and in fact, we have the first two readings up. The big problem is going to be my book, but we'll work around that later because that's supposed to be on reserve. But the packets are supposed to have been taken over there. They may not have been there early in the morning, so it depends kind of what time. There was a message kind of in the middle of it was kind of a message in the middle of the day that I kind of got that supposedly things were there. But anyway, hopefully you can get them. But you can have access to if you don't get the packets, the readings are accessible, and they've always been accessible. You can use JSTOR and just pull them out of the library. But I may just put them up here too. So in any case, good luck with all that. Are there any other questions before we get going here? And so I'm kind of curious, how many of you are planning to stay in town versus go home? Let me ask, how many of you are planning to stay in town? I'll do it that way. See Cal and CJ.
I'm going to stay in town.
Yeah,
So
I'll be in town.
Mason and Noah, are you guys staying or going?
I'll be in town.
I'll be in town.
Okay, everybody's staying in town. All right. So, I don't know what's going on with bookstores and other stuff, but all right, you'll be around. Okay. Well, let's get going here with this lecture. So, we pretty much. So, Noah, you missed. We're basically covering stuff that's in the mathematical appendix, chapters 26, 27, and we basically did linear algebra. And the main thing that you haven't seen, which is not in there, is how to take determinants, and particularly how to take determinants of the 2x2 matrix. And maybe I'll have to send you something on that privately. But that's something you're going to need to know. Also, I will note I hadn't looked at that for a long time. As a minor thing, he puts matrices into big parentheses rather than brackets. But I would tell you that most mathematical presentations put matrices in brackets. This is a trivial matter. All right, let's move on here. So, all right. So now we're going to do some set theory. So a complement set. So here you're gonna have practice in seeing some of these mathematical symbols. So a complement set of a set A in Rn, that's n-dimensional real number space. See, Rn, that means n-dimensional real number space, is Rn, and that backward slash means not. So it's Rn not A. It's all points that are in Rn that are not in A. Okay, that's a fairly straightforward concept. Okay, now we have a very important concept that we're going to use for sort of defining a lot of other things. This is the concept of a ball. Actually, in a one-dimensional space, it would be just a little segment, a segment of a line. If it's in a two-dimensional space, it's going to be a circle. If it's three-dimensional, it'll be a three-dimensional ball. As you go to higher dimensions, well, it'll be a higher level dimensional equivalent of a ball. Okay, so a ball has a radius, E, and it's defined as a central point. Okay, that X is a central point. We have a ball of radius E at X, that is the central point, and it's written as B sub E, so the sub E is the radius, and then in the parentheses, the X is the central point. And that's the points, all the points Y, such that Y minus X is less, the absolute value, that's the absolute value. The absolute value of Y minus X is less than E, okay? So in effect, that just tells you, if you're talking about a little line segment, so it would be, if E was a half, then the ball would actually be the 0 to 1 line segment, not including the endpoints. If E were a quarter, it's a line segment, then it would go from 1/4 to 3/4. If E was 1 over a Google again is 10 to the 100th, which is a huge number, so 1 over a Google is incredibly tiny. By the way, here's how big a Google is. It's probably, the last time I checked, it's more than the number of subatomic particles in the known universe. The last estimate of the number of subatomic particles in the known universe that I'm aware of is about 10 to the 84th or 5th or something like that, which is way smaller than a Google, okay? Really, I mean, that's like less than a quadrillionth of a Google. So anyway, so 1 over a Google is an incredibly tiny distance, but you could have a ball, you could have the line segment. You could say X is 1/2, there you are, and E could be 1 over a Google. So there you would have just an incredibly tiny ball with a radius of 1 over a Google. So that's what's going on there. And in fact, one of the things that we will be doing with these balls is imagining the radius getting smaller and having things happen. So radius going down towards 0. So you're getting down to things like 1 over a Google and even 1 over a Googleplex. By the way, does anybody know what a Googleplex is? Speaking of really large numbers. Somebody knew what a Google, Cal, you knew what a Google was. Do you know what a Googleplex is? And by the way, the number is not spelled the same as the company, although obviously the company. It's actually GOOGOL is the number, obviously it's LE at the end for the search engine.
I'm going to say
what a Googleplex is?
I'm going to say 10 raised to a Google.
You've got it. That's right. Yep. So, 10 to the Google, which is, that's a really huge number. And 1 over that is a really small number, but still greater than 0. I won't tell you about non-standard analysis right now. Later, I'll tell you about non-standard analysis. Okay, so a ball is an important concept. Okay, now we have an A is an open set. A is an open set. Okay, that symbol there, that upside down V with a line across means for all. I showed that in parentheses, but later I'm just going to use it. So if for all X in A, there exists a ball, here we are using this ball concept, around X in A, okay? Now, it might be that ball might have only a radius of 1 over a googolplex, okay? Now, what's the crucial thing about it? It means that it does not include its boundary, right? So there's some little space. If you have an open set, then every point in the set, there is some sort of little space between it and the boundary. The boundary is not a part of it, and that's the crucial thing. This is a way of defining not having the boundary. So you can get closer and closer to that boundary. You can be 1 over a googolplex away from the boundary. So you're really close, but you're not there. There's still some points that are 1 over 2 times a googolplex that are, in the set, but, closer to the boundary than you are. In a minute, I'm going to draw pictures of these things. So I'm going to use the webcam in a minute. Then the opposite of this, A is a closed set. These are sets that include their boundary. If the complement is an open set, so if n-dimensional real number space not in A is an open set, and what does that mean? It means that A contains its boundary. Okay. So let me actually, I want to use the webcam for a minute here. I might mention 5 and 6. So 5, a sequence is convergent if xi goes to x star, if for all e in 0 there exists an m such that for all I greater than m, xi is in the ball x star. So sequence is convergent. That's exactly this business of you can make the ball smaller and smaller. The ball can get smaller and smaller going to 0, and you head to a point. Okay, so I'm going to show you these sets. So in fact, well, let's just use the. Can you all see it?
Oh, no.
Does everybody see the webcam?
I don't.
See my hand?
No.
No? Yes?
So, Professor,
Hello?
there's this gray hex like pattern that's covering the whole screen for me.
Uh-oh.
Yeah. I can see it now.
Well, we don't have it up. Do you see it now?
Okay. Yes. Yes.
Yes?
Yes.
Is everybody else seeing it? Cal is saying he sees it.
Yeah.
Okay.
Mason, do you see it?
Yeah, I see it.
Okay. All right. So, well, let's just use the 0 to 1 line segment as our set A to keep things simple. So an open set, what's going to happen is this is 0, this is 1.
You need to make sure that's the you want.
Whoops. I think, okay. Whoops.
Keep going.
Wait a minute. I wrote and I don't see it. It's not visible. What the fuck? Excuse me.
See it.
Oh, this is not working. Yeah, I can see it, but it's barely. No, let me see if I got a blacker pen. I might have to use the whiteboard after all.
It might be because the overhead light is too bright.
Okay, let me shut off the overhead light. Let's see if that works. Yeah, that might help. I'm getting I think maybe a darker pen here. All right. Okay, let's try again.
Yeah, that's fine.
All right. So those round circles, those points, those are actually the boundary. Actually, let's think about a circle. So a circle with all the interior. Okay. So these are open sets. Okay. They do not include the boundary. In the case of the interval from 0 to 1, the 2 endpoints, 0 and 1, are the boundary. They are not in there, but everything between 0 and 1 is in there. Or in this case of a circle or something that's close to a circle, everything in there is in it, but the boundary is not. The closed sets are going to be the opposite, okay? So then we're going to include the 2 endpoints on that 0 to 1 interval, all right? Or if we've got a circle, I'm going to do that over here. We're going to include, so these are closed sets. They include the boundary. By the way, number 6, which we haven't gotten to, says that within a closed set, every sequence will have a convergent subset that will converge to some limit. You get, and that suggests because you've got the boundary, you can go to the boundary. But let's be very clear, very important point here. Not all sets are either open or closed. Okay. By the way, of course, in the case of either an open or closed set, the complement of that in that dimension will be the opposite. So the complement of this is going to be 1 out to infinity and 0 off to negative infinity. Okay. And that will be a closed set because the boundary of that set is going to be 0 and 1, and that'll be in. But down here, it's the opposite. A closed set. The complement is going to be everything above 1 out to infinity, and everything below 0 down to negative infinity, but it will not include 0 or 1.
I'm in class right now.
Which is the boundary. So if you're dealing with an open set or a closed set, then the complement is going to be just the opposite. But you should be aware that not all sets are open or closed. The fact of the matter is, I mean, you can have a set like, well, to give these, you can have sets that are not either, and then the complements will be not either. So an example of a not either would be one that has 0, but it doesn't have 1, okay? Or you could have a circle that's got half the boundary, okay? So not all sets are definitely open or closed. They can be half-assed. They have part of the boundary, but not the rest of the boundary. In that case, then neither the set itself nor its complement will be open or closed. All right. Okay, I'm going to get off the webcam. I'm not quite sure how do I get out of this and go back where I was. Share. Okay. This is the first time I've used this webcam, guys. So I'm she used to do this all the time, but I'm stop sharing. So okay, we're back. All right. Okay. So we had some convergence properties. Number 5, the sequence is convergent if x with superscript I indicates a sequence as I moves up from 0 on, integers, whole numbers. It goes to x star, it's convergent to a point, x star, if for all e greater than 0, there exists an m, such that for all I greater than m, the xi's will be in the ball. So you're going to be, the sequence is going to be getting closer and closer and closer. It may never actually, here's an important point about convergent sequences, they may never actually get to that point, okay? They might get to that point. But they might not. They may just get closer and closer and closer. 1 over Googleplex, and 1 over Googleplex to the Googleplex, and so on and so on and so on. But they may never actually get there. You just keep going up. But you can just keep getting smaller and smaller balls, and further and further out, and it'll get closer. Everybody got that? Got that idea? Yeah. CJ.
Professor, could you please remind us what that symbol? I'm not sure if it's an epsilon or perhaps a sigma. But could you remind us what that is?
The upside down V or the backward looking capital E?
The rounded E, normal facing rounded
that's
E.
what that means, belongs to.
Belongs to? Okay, thank you.
Yeah, it belongs to a set. Okay, so X and A, in the case of this one, it's the sequence XI, or I above this M, will be in the ball E, of radius E, with X star at the center, the point that it's being converged on, okay? Yeah.
Okay, thank you.
Yeah, this is useful to figure out what's going on here. So in fact, well, I guess you can't see my finger pointing at it, but let's go through that sentence again. So the sequence is convergent if XI is a sequence, and I is going to actually start with 1, and it's going to go up, just counting. And as you get higher, it's getting closer to X star, a point. If, and then that upside, that V with a little line across it means for all. So for all E's greater than 0, but that might be a very small E. It might be 1 over Googleplex. It might be a really small number, but it's greater than 0. There exists an M such that for all the I's greater than that, farther in the sequence, the rest of the sequence, XI, for I above M, that's the end of it, will be in that ball, with X star at the center, and epsilon, or E, it's not epsilon, it's E is a radius. The member thing is actually epsilon, but that's, so XI, the rest of that sequence, the later part of the sequence is in the ball, okay? Is that everybody clear what's going on here? You all hanging on here? Anybody need any further clarification? All right, then the final one, A is closed if every convergent sequence in A converges to a point in A. So that's a sort of basic fact about closed sets. All right, we're going to move on to the next slide here. All right, more set theory. All right, A is bounded. Is a bounded set if there exists X and E such that A is in the ball of X of radius E. Okay, so what this says is that, now this is going the other way. And when we were talking about convergent sequences, we were thinking about balls getting smaller and smaller and smaller, and we could get the sequences further out, still getting into that ball, approaching, squashing down to the point, the convergent point. Now this is going the other way. Here we may be having to get a really big E. It might be a Google or a Googleplex. Okay, so A is a bounded set if there exists some point and an E, which might be a Googleplex, a really huge number, but the entire set A is contained within the ball centered on this point X. There's going to be probably a point in the set, although maybe not, depends on the set. If the set's a donut hole, the point X might be in the middle of the hole and it's not in the set. Okay, but in any case, we've got some point X and we've got a ball with a radius, a finite radius. It might be a huge radius like a Googleplex. But we got a ball, we create a ball, and the entire set is in there. The point, the opposite of being bounded is that the set is running off to infinity in some direction, in some dimension. Okay? That's the crucial thing. So the bounded set, and presumably a bounded set has a boundary also. So note that if the set contains its boundary, it's closed. If it does not, it's open. And here we have the point that we just made, that there are bounded sets that have a boundary, but they are neither open nor closed. We saw some pictures of those, like the unit interval from 0 to 1, where 0 is in the set, but 1 is not in the set. That's neither open nor closed. Or a circle, it's half the circle is in the circle with its interior, but half the circle is in, and the other half the circle is not in. And those are both sets that are neither open nor closed. All right. So everybody got boundedness. So basically, it doesn't run off to infinity in any direction. We're talking about n-dimensional sets here. So it may be we can have a set that's got a Google dimensions. Okay. And it might be that it might be in fact that it's bounded in a Google -1 dimensions, but there's one particular dimension somewhere where it goes running off to infinity, and then it's not bounded. Okay. Everybody got this? And this is fairly intuitive. Boundedness is pretty important. Hey, this is in fact very important. Cal, you got a question?
So,
you raising your hand, or you just
yeah.
with your glasses? You got a question?
Yeah, you got me. So when I see in the very first sentence of number 1, what is it? A or what is it? Belongs to a set B sub V of X. What is B sub V of X supposed to stand for?
Ball. This is for ball. So ball of radius E centered on X.
Gotcha. Okay.
So BEX is a ball of radius E with X at the center. Everybody got that?
Yep, got it.
Okay. So I think boundedness, and of course boundedness is completely central to microeconomics, because the whole point is we've got all this, what is the central problem of microeconomics? It's people trying to optimize things, and the producers are trying to maximize profits, consumers are trying to maximize utility, but they're all doing so facing bounds, okay? Producers are facing bounds of technology and inputs, and consumers are facing budget constraints. So all these constraints, it's all this constrained optimization, well, those are bounds. So we're, basically all of microeconomics is dealing with bounded sets, okay? All right, now we get to a rather important one, compact sets. A is a compact set if it is both closed and bounded, okay? We had closed. So what does it say? It's bounded and it includes its boundary. That's a compact set. This is going to be important in a minute. Then it also happens to be the case if A is compact, then every sequence in A has a convergent subsequence. All right, here we come now to a very important concept. Most of microeconomics, when this does not hold on sets that we are dealing with in microeconomics, then things get complicated and messy. This is the idea of a convex set. So A is a convex set if 2 points in A, x and y, and we have a number between 0 and 1, t, then what happens is that basically we're describing this tx plus 1 minus ty. That is the line segment connecting x and y. That's in A. Okay? That's convexity. And this important type of set for economics contains all line segments between any 2 points within it. And failures of convexity, in fact, convexity lies behind a lot of so-called economic laws and assumptions we make about things, such as the law of diminishing marginal rate of substitution, which in simple cardinal utility is the law of diminishing marginal utility. Or the one actual economic law that really does seem to be true. Actually, I'll throw it out to you. Anybody want to guess? I'm gonna get the webcam up here again in a minute. But I'm gonna ask to see if anybody does anybody know what there's a whole lot of so-called economics laws, but I'm aware of only one that actually, as near as I can tell, is absolutely, totally universally true. I've never, ever heard of anybody coming up with a counterexample or a weird case. Anybody, law of diminishing marginal utility does not hold universally. Addicts, irrational addicts, they start getting something and they want more and more of it. Okay, they get more utility for later editions. So the law of diminishing marginal utility is not universal. There's a whole bunch of laws. The law of supply and demand, it doesn't necessarily hold if you got badly behaved supply and demand curves. So there's all sorts of so-called laws that don't. The law of demand, the demand curve slope downward. No, I got Giffen goods. There's the law of demand curves can slope upwards. So there's all kinds of so-called economic laws that, yeah, they're true a lot of the time, or maybe most of them, but they're not universally true. There's exceptions. There's counterexamples. Anybody know of a law that's on the supply side? In fact, I even mentioned it.
Perhaps law of diminishing marginal returns.
You got it, CJ. Very good. That is it. So, that's the old classical formulation of it, to be a little more precise. The way we're going, the law of diminishing marginal product. Okay. Now, the law of diminishing marginal product, because what does that say? That says that after some point, adding more and more of a factor of production, holding all the other factors constant, you start to get smaller and smaller additions to output. Or if you want, the partial derivatives of production functions beyond some point become negative. Second derivatives. It doesn't say that it's always negative. You can have positive, you can have increasing marginal products for a zone. For example, in agriculture, if you're thinking about growing a crop, and you're thinking about putting seed in the ground, okay? You've got a field and you're planting seed corn. If you just put a few seeds in the ground, you may not get much of a crop because the plants have to germinate. They have to have sex. You have to have plant sex, okay? And it takes a certain amount of plants in the field. They have to be close enough to each other to communicate and fertilize each other and germinate, okay? So at an early stage, as you start adding more seeds to plant corn, in fact, you get increasing marginal product as you start to get more and more germination. But there'll be some point where you finally get enough, plants in the field that you're getting full germination, and that will give you an inflection point where the curvature of the product curve will change. And then after that, as you start adding more and more seeds, you're going to get smaller and smaller additions to output. The field's going to get filled up with corn, and you're not going to get, in fact, that kind of a product curve will, in fact, probably be an actual maximum amount of corn you can grow in the field. So you can have a period of, but I know of no exceptions to the law of diminishing marginal productivity. Somewhere along the line, if you're holding all the other factors constant, you're going to reach a point where that second partial derivative on that factor is going to go negative. You're going to get smaller and smaller additions to output as you pile more and more of that factor on the other factors. It's going to stop producing more. Okay. Anyway, if any of you come up with an exception, we can write a paper and get it published in the leading economics journal, okay? So I invite you to think about it, see if you can, but every other so-called economics law that I've heard of, there's a whole bunch of things that have had a law of this, the law of that out there. They've all got counter examples and exceptions, but that one seems to be absolute. Anyway, but that's dealing with with convexity. Actually, I think. All right. Okay. So we're gonna look at this a little more closely, because this is a very important concept, and it really is tied to concavity and diminishing marginal products and marginal utilities and marginal thises and marginal thatses. So we're going back to the webcam here. Okay. All right. Let's see. We'll do more on the lower part of the page. Can everybody see this? Hello? Does everybody see the sheet of paper? I'm not hearing anybody say anything.
No. Sorry. We think you can see our pictures on the WebEx call, but yeah, no, I can't see anything. It might be like a anonymity thing where they let you like block your screen so that we can't see it. So I think you can probably change that. I'm not sure. I've seen my teachers in other classes do this.
Yeah, obviously, I'm behind on this sort of thing. So. Mm-hmm. We'll get this figured out. But we did it once here, so we get it again. Can you see it now? Whoops.
No, I cannot. So I'm going to screenshot what I'm seeing. I'm going to email it to you right now.
Let me just say, if you see it, say yes, or say I see it. We're trying various things here, so I should say Marina is trying various things. I'm very appreciative of this.
Try switching to share content instead of share what was already on.
Yeah, that's what I'm trying to do.
Share content. That's the top there.
Yeah, we're in business.
Is that it? Do you see it?
Yeah.
There we go.
Okay.
Mostly.
All right. Okay. So, well, as a matter of fact, an example of a convex set is that line segment, and also the circle. This is convex, and that's convex. Let me show you what's important exceptions to convexity. All right, so here's where convexity gets important. Let's think about indifference curves. So I'm going to draw a regular, well-behaved indifference curve. Oops.
Is a convex set a type of compact set?
They don't necessarily. No, a convex set does not have to be compact. It doesn't have to be bounded. It does not have to be bounded. A convex set will have. Well, actually, it doesn't even have to be closed. It can be open. It can be closed. It could be neither. It could be unbounded. All that matters is that the line segments. If you take any 2 points within the set and you draw a line segment between them, the line segment will be in the set. But that could be an open set, that could be a closed set, that could be a partly open, partly closed set. This really has to do with the shape of the set, that's what it is. You want the shape of the boundary of the set, okay? But it might not be a bounded set. It could go off to infinity in one direction, but it's got some kind of a bound. So it really has to do, I'm going to draw this in a minute, you'll see, it really has to do with the behavior of the boundary of the set. So, well, I'm going to give you examples and you'll see this better, okay? So I'm going to show you something. I'm going to show you, this is economic theory stuff. I'm going to show you sort of the standard story where we have convexity, and then I'm going to look at something that doesn't have convexity, and we'll see why it's important, okay? So I'm going to draw an indifference curve. So we're doing the demand side. So this is the kind of thing that I was not very good with those darn. So now we're going to define something. I'm going to call this the upper contour set. The upper contour set are the set of points. So this is some level of utility. Let's just call it Ux. But we're going to look at all the points that are at least as preferred that are to this of x to count. So that's going to be all these points up here plus that indifference curve. So the indifference curve is the boundary, okay? But this is an unbounded set. It goes off in that northeast direction, okay, to infinity, okay? So it's not a bounded set. This one does happen to be closed, although it might not be closed sort of, in fact, it doesn't really have to be closed. That's less important. So, but here's the point. So let's, in fact, what we're interested in really is, let's take 2 points on the boundary here on the indifference curve, and we draw a line segment, okay, and that's in the set, okay. And what does that tell you? That tells you about the curvature of the indifference curve. That's what it's telling you about, right? That's what it's showing. Now, can anybody tell us what does that curvature mean? What does that show about the respective marginal utilities for those two goods? The ratio, this has to do with the ratio of the marginal utilities of x1 and x2. As you vary x1 and x2, what's happening to the ratio of their marginal utilities? Or actually, yeah. In fact, let me define something else. What we have, the slope, the tangent line slope of this is going to be the marginal rate of substitution, MRS. Marginal rate. The marginal rate of substitution is really given by in a cardinal utility world, is given by the ratio of the marginal utilities. Okay. But we're doing ordinal utility, so we don't really actually have to refer specifically to the ratio of the marginal utilities. But that's basically what it is. So that slope tells us how I could trade those goods off and be equally happy, okay? If x1 is corn and x2 is peas, at that particular point right there, this slope tells me how many peas I would give up, how much corn I would need to give up some peas and remain indifferent, equally happy, okay? That's the marginal rate of substitution, yeah, right?
Yeah.
So as we move along here, we've got a change in the marginal rate of substitution. We go to here, and that slope changes.
And slope decreases.
Yep. In fact, this is known as well, we could call it the law of, but I'm putting that in parentheses because it may not be true, diminishing marginal rate of substitution. Right, it is MRS. And this is the ordinal utility equivalent of the law of diminishing marginal utility. Okay, we're not going to use cardinal utility. We're going to do ordinal utility when we get demand theory. We're going to be operating with all these indifference curves. And basically, the convexity of this upper contour set gives us this shape along this indifference curve. So as the indifference curves look like this, these indifference curves are going to give us this law of diminishing marginal rate of substitution, which is the equivalent of our good old garden variety law of diminishing marginal rate of substitution. So let me show you what happens if we don't have convexity. Okay, I'm going to show you an example on the supply side too. It messes things up. It means a failure of this. So if we have a non-convex upper contour set, we're going to have an indifference curve that looks like this. All right? This is not, okay, this is convex. This is not convex. Okay? So let's take 2 points. Let's take those two right there. Okay? Take the extreme ones. Except for the 2 points themselves, the entire line segment is not in the set. Okay. So let me give you a general example. You gotta think of non-convex sets. They look like, they can look like that, you know, or they may have holes in them, like the donut. Oops. These are non-convex sets. Or on the 0 to 1 interval, we have a 0 to a third, and then 2/3 to 1. Okay, these are all non-convex.
So, Professor,
they've got holes in them, right? What? Yeah.
So, is a non-convex set by definition concave, or is that also?
No.
Okay.
No. Again, this is a totally concave one. Would I hate to, okay. There's your concave one, okay.
Right. Yeah.
But their sets can be neither just like with openness and closeness. You got this one is neither. It's neither convex nor concave. Okay. Now, so this is what's going on in here. This is a zone where there's a failure of the diminishing marginal rate of substitution. Okay. So this is a zone where somebody, in effect, suddenly they start to want to have, they're liking to have more and more of the good. They've got some, if you want to think of it as sort of addictive behavior or addictive personality or something, they're getting more and more of this, and they're willing to give up more and more of one good to get more units of a single good. And that is represented by this badly shaped indifference curve, okay? Did they show you this kind of thing in intermediate? Probably not. They were too busy just teaching you about well-behaved standard indifference curves, okay? But this is, now, okay, let me throw it at you. What does this imply about, can anybody figure out what this would imply about a demand curve? If you were to do a demand curve derived from an indifference curve that looks like that doesn't have this, that has this non-convexity to it, what will the demand curve look like? What's going to happen to the demand curve? You may have forgotten that demand curves you're going to be doing price lines. So you get to one combination of x1, x2, and then what's going to happen as this price goes from that to, you're coming down here, and then you get to this line, and then you start going there. What's happening? What's happening to the price combination? What do? You jump from here to here, right? So what just happened? What does that make your demand curve look like?
Nonlinear?
Well, it might be a straight line. Well, it's not one straight line.
It's gonna have a gap, right?
It's gonna have a gap. It's got a discontinuity. It's gonna have a big hole in it. You're never gonna see x2 in this zone or x1 in that zone. You're gonna suddenly jump from this combination of x1, x2 to that combination of x1, x2. Let's see, going further down here. You're going to get a demand curve that will look like something like that. It's coming down and whoops, bum, 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 bum. And then it's got a big hole in it. Okay.
So it looks like a piecewise function?
Well, this doesn't look like a supply function. This is a discontinuous demand function.
No, a piecewise, like it's where it's
why might this happen? Well, there's various reasons why this might happen, but it might happen because of non-convexity of preferences that people have, or if this is an individual person's demand curve, it might be because they've got this zone where they've got an addictive personality that kicks in. They've got a violation of the law of diminishing marginal utility, or in this case, the law of diminishing marginal rate of substitution. By the way, we often tend to think of that as being irrational behavior. When people get obsessed with things, that's sort of irrational. It's not rational. People don't do that. They're being obsessive and weird, and it's although we can argue about whether that's good or bad. But in any case, for a lot of things, that's not good. It can lead to bad behavior. But in any case, you get this. So note what this suggests about equilibrium. Suppose the supply curve goes through here. Do you have an equilibrium? No.
No.
No, you don't. Okay, so non-convexity, failures of convexity can destroy the existence of equilibrium. Okay, I think I want to go back. I should figure out how to do this. Why don't you tell me what to do here? So stop sharing. Where do I stop sharing? She's going to point to me. I'm going to try to do this. Point. Let me do it. Let me do it. You show me. To those dots.
Yeah, that's control panel. Stop sharing.
I hit share. Stop sharing. Okay. Oh, we're back. We're back.
Yeah.
Okay. Do you guys think you got the idea of convexity? Sort of, more or less.
Yeah.
Oh, I was gonna give you another example. I'll tell you. I'll just verbalize it. Think of. No, that's all right. I can put it later. I'm going to be using the in a minute. But if you think about economies of scale, is another failure of convexity or production function. Okay. If you have economies of scale, you're going to have a failure of convexity. Let me ask you the following: think about a production possibility frontier. The production possibility. If you think about a production possibility frontier, okay, the standard one, it kind of goes, it's bowed out, right? And you have this production possibility set, which is going to be the production possibility frontier plus all the points beneath it. That's a convex set. Okay. Suppose for both of the goods you're looking at, and you might have actually had somebody throw this out at you in intermediate micro. Suppose both goods have economies of scale. What is the production possibility frontier going to look like? Anybody got an idea? What's production possibility frontier going to look like if guns and butter, if you're doing a guns, I don't know if they still do those guns and butter things. If it's guns and butter, or if you want to be abstract, peas and corn, X1, X2, suppose they both have economies of scale. So if you double the inputs, you more than double the output.
Is it going to be a very steep one because they're going to favor whatever, say, the guns are?
You're sort of getting somewhere. You're trading off the goods.
Yeah.
I'm going to ask you, what is the shape of the production possibility frontier? Think about that.
It's a gradual curve.
Gradual curve?
Well,
Oh, you don't have it. Come on, guys. No, you're hiding. You got it? Somebody should have told you about this somewhere in earlier micro courses, although probably just as a kind of a throwaway. But maybe not. It's an oddball thing. It's going to bend inwards. Bend inwards.
Okay.
It's not going to be bowed outwards. It's going to be bending inwards. So if you're thinking about the production possibility set as the points below it and suddenly that production possibility set is now not convex. Okay? Another failure of convexity. All right, so we're going to move on. All right, so there's we need to move on. Okay, so there's another entry. So yeah. Cal,
Professor, I do have a quick question because maybe my understanding this is too fundamental, but so I kind of just right here you can see this is generally what a production possibilities frontier looks like, correct?
Right.
Wouldn't that be concave?
We're looking at the production possibility set. We have
the set. Okay.
So the set is the set is given your technology, given your resources. What are the possible combinations of output you can produce? And you can produce everything below the production possibility frontier and everything on the production possibility frontier. What you can't do is produce stuff outside of there. That's a limit.
Yeah.
Okay. And if you don't have increasing returns to scale, actually, if you have constant returns to scale, the production possibility frontier will be a straight line. Yeah. But that'll still give you a convex set. Okay. But if you have increasing returns, if both goods have increasing returns to scale, it's a little complicated if one does and the other one doesn't. It depends. Depends on the balance.
Yeah.
But if both goods have increasing returns to scale, that production possibility frontier will bend inwards, and the production possibility set that lies below it and includes it will not be a convex set. And in fact, that creates economies of scale creates problems. In fact, creates problems to the existence of a competitive equilibrium. If you have unlimited, in fact, let's get to real economics, okay? Simple, basic, this you probably know. Suppose you've got a sector that's got unlimited economies of scale. Are you going to have a competitive equilibrium in that sector? I see Cal at least shaking his head. Anybody else? CJ shaking his head. CJ, well, Evan, you tell us. Evan, what happens if you've got unlimited economies of scale in a sector? If in a real world, in a market, suppose you just let it happen. What are you going to end up with if there's no government intervention? You just laissez-faire, let the market do its thing. What are you likely to end up with if you've got unlimited economies of scale in the market for widgets?
Whoever gets there first will just dominate, essentially.
What's going to happen?
Whoever gets there first will dominate.
And what are you going to end up with? What kind of a market structure? Are you going to have a competitive market?
Monopoly.
You're going to have a natural. In fact, this is the natural monopoly case. You're going to end up with a pure monopoly. Whoever gets to be bigger than everybody else can undercut them in price. Will have lower average costs. Okay, that's one of the flip sides of increasing returns to scale. In terms of average cost curves, you have longer and average cost curves are just declining all the way. So whoever gets to be Mr. Big, whoever gets to be bigger than the others can undercut them in price, can charge a price that's where they make a profit, but everybody else is losing money and drive them all out of business, and you end up with a pure monopoly. And in industries like that, like utilities and some others, you've got a public policy problem. Do you let there just be as a pure monopoly? Do you regulate the monopoly, or do you just have the government take it over? It's a public policy issue because if you leave it alone, well, you may end up with this pure monopoly. Now, you may say the pure monopoly is okay, but it's a policy issue. You won't have a competitive market. All right. Anyway, so convexity is very important. Convexity actually has relevance. It's actually important in the real world. Okay. The real economic world. Okay, let's move on. All right. Okay, we have continuous functions, and Brouwer's fixed point theorem is not in the mathematical appendix. It's in the text when they need it, but I'm going to give it to you now, and we have almost all what we need for it. All right, but what we further need is continuous functions. So we're going to have continuous functions and Brouwer's fixed point theorem. So a function is continuous at x star if for all sequences xi that approach x star, then the sequence f of xi will approach f of x star. And this, I think, is something you know intuitively what this is. It means the graph can be drawn without lifting your pencil, your pen, or whatever it is you're drawing with, or your computer pencil. Okay. Now, let's note, continuity is necessary, but not sufficient for being able to differentiate, to take derivatives, which we're going to be getting into momentarily. To differentiate at f of x. To differentiate, you have to have smoothness. Okay. All smooth functions are continuous, but not all continuous functions are smooth. How could they be not smooth? If they have a kink. So if a continuous function has a kink at x star, you can't take a derivative at the kink. Yeah, Cal, you raised your hand. Did you raise your hand? Or
yeah. No, I was just saying, like, I mean, do you only really see that when there's an absolute value in play, or can that occur?
No, it has nothing to do with absolute values.
Okay.
No, we will. I mean, the issue of kinkness is something we will. That's something that's going to come up. I mean, in fact, I told you about this. I think the first day. Here's an example that's sort of okay. When we get to talking about prospect theory, there's this idea that people this business of the endowment effect, that people don't like to give things up. Okay. If you have something, you don't like to give it up, okay? Yeah. So what that really implies is, people that, okay, I want a little more of it. Okay, I'll have a little more of it. But boy, I really don't want to give it up. If that's the way people think, and there are a lot of people for whom that's true, what that suggests, thinking in terms of a utility function, the utility function's got a kink at the point where someone is located. Oh, I want to get a little bit of extra happiness, extra utility from getting more of whatever this is. But boy, I'm going to be really unhappy and pissed off if somebody comes and takes it away from me, okay? By the way, well, let's not get off to it further. In any case, but, there are certainly, functions of interest that have kinks. And at a kink, you can't take a derivative. You can't differentiate. You can't do calculus. But that's a continuous function. Okay? But all smooth functions where you can take derivatives, they're also all continuous. You got a discontinuity and you can't take a derivative either. All right, so, okay, now we're going to do Brouwer's fixed point theorem. So Brouwer's fixed point theorem, it's really pretty easy to state, okay, but I'm going to have her come back and get the webcam on again in a minute. But here's what it says. Brouwer's fixed point theorem states that if A is compact and convex, okay, this only works for convex and compact sets, and we have a continuous function f that maps A into itself, and it's continuous, then there exists an x in this set such that x equals f of x. All right? That is Brouwer's fixed point theorem. It's pretty simple, really. And we'll note that this is the crucial theorem for proving the existence of competitive equilibrium. Now, before I show you some pictures, let me note that when we get to when we prove the existence of general equilibrium, I'll do it for a simple pure exchange economy, and I will use Brouwer's fixed point theorem to do it. Okay. But if you look at the more general proof of the existence of general equilibrium that was done, there were two competing ones actually, but they both relied on the same thing. In 1954, the more famous one is by Kenneth Arrow and Gerard Debreu, the Arrow-Debreu existence theorem. A man named Lionel Mackenzie had a rival. He kind of got screwed by history because he actually did his first. But Arrow-Debreu, everybody talks about. People who are careful talk about Arrow-Debreu Mackenzie, but most of the people talk about Arrow. But in any case, they didn't use Brouwer. They used a more generalized form of the fixed point theorem that we're not going to get into, called the Kakutani fixed point theorem. Kakatani is a more generalized version of Brouwer, but the idea is basically the same. Okay, yeah, I'm gonna, now we're gonna get back to the webcam here. Okay, hopefully we can get here. I'll show this, show how this works with some. Hopefully we can get here. Real quickly. All right, are people seeing this? Can you see the web? Can you see the paper? It's Cal's got his,
Yep.
somehow Cal, I see you, but nobody else. I'm not sure why, but this is maybe because you talk. Okay, so I'm going to do it very simple. So let's do Brouwer. So we have F A into A, and A is compact. This A and F is continuous. We don't have too many conditions on this. And F is into A, and it's compact and convex. So we're going to use a simple, let's let our set be, let's let A be the closed interval, 0 to 1. Okay, we already know that in fact it's compact, it's bounded, and it's closed, and it's convex. Okay, it's both compact and convex. So for mapping that into it, what are we looking at? We're looking at functions that go from 0, 1 into 0, 1. So we're looking at functions that are going through this this box. Now let's think about where is the set of points where x equals f of x. That will be the 45-degree line. All right. So this is f of x. This is x. The horizontal axis is x. The vertical axis is f of x, and the 45-degree line will be the set of points where x equals f of x. So what does this say? This says if we have a continuous function covering this whole space, it's got to cross that line somewhere. Okay? Okay, so looking at this, we can figure out why we need these conditions. Suppose the function is not continuous. Well, if it's not continuous, it can just, jump over that line and, skip it. So F's got to be continuous. F's got to be bounded. If it's got to be closed and bounded. It's got to be bounded. If it went off to infinity, well, F could just, head off and never, stay above there. It could be an exponential function or something. Something just flies off into infinity. And it's got to be closed. If it's not closed, this is a little more subtle. Suppose these points, let's suppose that point there is not in. Suppose it's not closed. What can happen is that the function can, then that means that point is not in. This function could just go to there, can converge on that point. All right? But you get to that point and bingo, you're not there. All right? So those are the main exceptions. Okay? So in some senses, it seems like a pretty simple theorem. It's a very deep theorem, but it's in many respects really quite simple. And again, I gave you some examples in the first lecture, so let me remind you of some of those. The one is I actually have. I'm finishing my coffee. I'm stirring my coffee, and if you stir your coffee in a regular way, there'll be one point that's not moving. You can think when you're stirring coffee of mapping the old surface into this new surface. Well, one point doesn't move. I mean, it's compact and it's bounded and convex, and the stirring is a continuous function. One point doesn't move. Or your hair, you comb your hair. There's going to be one point where it's no hair going over it. And then I also gave this other one of you drive from your place here in Harrisonburg to your, I don't know if you live in Northern Virginia, the rest of them do. Anyway, so someplace, let's say, to your home, wherever it is, and you leave at a certain time of day, and you get there at another later time of day, and then the next day you turn around and start at the same time of day you started, take the exact same route. and get back to where you were the other day before, arriving at the same time. And there will be a point on the road where you will be at the exact same point on the road at the exact same time you were the day before. Okay? Those are all examples of Brouwer's fixed point theorem. It applies to lots and lots of things. And it was John von Neumann who first realized that this was very useful for proving. He actually originally thought of it for proving a game theory problem in 1928, and then he did it for a very simple model of it, general equilibrium. But then the first person to use Kakutani's fixed point theorem was actually John Nash, who did that when he proved the existence of the Nash equilibrium, and Arrow and De Broglie and Mackenzie all basically got it from Nash to use this broader type of fixed point theorem to prove the broader one. Okay, I need to go back now. Stop sharing. Let's see if I can do it myself. Stop sharing. Okay, we're back. All right, there we go. Okay. From calculus. Okay, if f is smooth, then derivatives can be taken, differentiated. The first derivative this is all pretty familiar, df of x star of dx. And that is given by the limit as t goes to 0 of f of x star plus t minus f of x star divided by t, which is the slope of the tangent line of the function at x. Okay. So I think you all know this. 2, more generally, whoops, I've got something in here. I don't know where that came from. Dealing with multiple variables, I got a couple of deltas in there that shouldn't be there. More generally, when dealing with multiple variables, and we look at marginal effects of changing one variable while holding others constant, we'll have the Cater's paribus conditions. Then we are dealing with partial derivatives. Okay, if you see D, then it's a total derivative. And of course, if you just have one variable, it's a total derivative. If you got more than one derivative, then you're dealing with partial derivatives. And when you're doing a partial derivative, you just change that one variable. So we have partial f of xi, and this is actually a cross partial. So we have partial f of xi changing xj. Okay, and you can look at this whole. You have a matrix df of x that gives the matrix of all the partial derivatives of every possible variable, and that's known as the Jacobian matrix J. And by the way, at an unconstrained maximum, the Jacobian matrix will be singular. Know what that means? Its determinant is 0. Okay, think of this at a scalar level. This is just the determinant, the derivative being 0. We define the matrix's second partial derivatives. The f of x is known as the Hessian matrix H, and whose elements will be partial derivative squared of f of x, and there's a cross partial xi, partial xj. So those are cross partial derivatives. And at a maximum, the absolute value of, we will have j, the determinant being 0, but the h will be negative semi-definite, okay, which we defined last time. No, we're going to have to go track that down. That's defined and varied. You can find that stuff, but that has to do with these. That has to do with you're going to need to get up on that. All right. Okay. Now we get to concave functions. So we're no, it's okay. So a concave function. If f is a function from the n-dimensional real number space into R, into the real numbers, it will be strictly concave if for t between 0 and 1, f of tx plus 1 minus ty is greater than t f of x plus 1 minus t f of y. And if this holds for, that's strictly concave if it's strictly greater than, if it's greater than or equal, then that's quasi-concave, which actually most of the time is good enough for us. If f is concave, then it's Hessian, its h is negative definite. And if it is quasi-concave, then the Hessian matrix H is negative semi-definite. You are going to be having to check this for the first homework problem, okay? The first homework, you're going to have problems where you're going to be looking for this. Now, here's a very important point. The set of points below a quasi-concave function will be convex. If it's quasi-concave, it might just be a straight line. Okay, but that's still going to be a convex set under there. So concavity of functions gets related to convexity of sets. All right, this is a very deep connection, and this is going to keep coming up and up. All right. All right, I have one more slide. This is kind of a couple of loose end points, and we'll stop at the end of this. So a couple of loose ends. Actually, I may for this. Well, let's see if I can. Anyway, I'm going to want the webcam. Before that, so separating hyperplanes. If A and B are convex and disjoint, meaning they have no points in common, then there exists a separating hyperplane, H of PA, such that P dot X is greater than or equal to P dot Y for all X in A and Y in B. And for H, P dot X equals A. We actually had that back the last time. Okay, I want to show this. We're going to do one more final webcam, and then we'll the final going out the door thing. We're getting near the end.
You go to share meeting?
Share.
Meeting.
Just share.
Meeting. Oh.
Share meeting. Whoops. Down here.
Mm-hmm.
Share meeting window.
Yeah.
Okay.
Okay. Yeah.
Whoops. What just happened? All right. Let's share.
Share content.
Share content. There we are. Okay. Whoops. Okay. All right. So I'm going to show you what separating hyperplane looks like. So let's say we got set A and we got set B. They're both compact, and they're disjoint. They don't share. So what does it say? It says you can draw it. In this case, a hyperplane just as a line. Hyperplanes are a dimension. You can. This is more dimensions. It would be a plane, not a line. You can draw some kind of a line or a plane that will separate the two sets. It's really pretty basic. And this will have this characteristic of P dot X equals A. A is going to be actually kind of the slope of that. So this is really pretty simple. But we use those later. Okay. Let's see. Go back. Stop sharing. All right, here we go. Okay, so the final point. We're not going to deal with this much, but this will help you. This lies behind the reading you have by me in the first section of the course. You didn't get that put up. We're not going to do a whole lot with these, but they're going to be popping up from time to time. And this has to do with dynamical systems. So what lies behind dynamical systems are systems of partial differential equations. I'm not going to make you ever solve any differential equations. PDEs, partial. By the way, if you take Q fin and you want to do the Black-Scholes formula, then you have to worry about PDEs. So anyway, a system of partial differential equations is given. Note here that P is a vector. All right, so we're dealing with multiple equation systems or multiple variable systems here. So partial f of P, partial pi equals a function gi of f of P and P with a boundary condition given by f of Q equals 0. Okay, and so when we talk about a dynamical system exists when you have F is a system of partial differential equations, and we have a state space S, and R is the real number line, and usually in these systems, R will be interpreted as time. Because differential equations are about things moving through time, right? Dynamical systems are about time trajectories of things. And there's a lot of people that say differential equations describe the world, okay? You want to describe physical trajectories of the world? Well, you see things moving through time. Well, we describe them by dynamical systems, okay? So the system can be given by f of xt, which is s cross r into r. And the system will describe time trajectories of the system. And these time trajectories can do all sorts of things. Dynamical systems may have equilibrium that the system converges to and stays. It may have an attractor point that it approaches that never gets there, it converges. Or it may go on limit cycles. Or it may have erratic it may have erratic patterns like chaotic dynamics and so on. So when you read my paper is actually about this, in the first part of this reading is about complex dynamical systems. And so this is what we're talking about. But I'm never going to actually make you solve any differential equation systems. So this is a bit of a kind of a higher level thing. But anyway, that's invariant there. So anyway, so I have completed now with 4 minutes left. I've completed what I was planning to talk about. So today. So are there any questions about what's been lectured on or anything else at this Labor Day weekend coming up? And anyway, anybody got any questions or comments here? Yeah, Cal.
Yeah, so Professor, will not being able to solve like partial differential equations like take away from our ability to do some of the sections within variant, or is it,
no, don't worry about it. No.
Okay.
No, I mean, there's some things in variant that there are some things that are in variant. I will confess that in some sense you're going to get variant a bit lightly. I think at the first day, and since Noah wasn't around for the first day, I'll repeat something I said, is that to some degree what this course it's partly a watered down graduate microtheory course,
right,
with all this extra stuff that you won't get in a grad microtheory course, because we're going to talk about all these things where things don't work right. They tend to play down in grad microtheory courses because they're trying to get you ready to pass prelims. Okay, so we're going to talk about all this weird stuff that doesn't work, and that's what's in the readings. The readings are all about all this other stuff, or some of the readings are anyway.
Okay.
The variant is kind of the straight stuff, but we're not going to do everything in variant. So we're going to be focusing more on kind of the easier basic stuff in variant. There's going to be stuff in variant we're not going to do. Most of that's tougher stuff. And so I'm not going to make, there's some things in the math, here's something, affine functions. So that's in the mathematical appendix. I'll just tell you that affine functions are kind of a generalized form of linear equations. We're not going to worry about affine functions. So there's some, and I haven't told you about the envelope theorem. Well, I might tell you about the envelope theorem, not formally, but informally. So there are things in variant we're not going to cover. I'm not going to, I'm not going to let you know what you need to do. So I'm letting you know what dynamical systems are, but to actually solve differential equations is a little hairy. There are courses, that's a math course. If you're a math major, you take differential equations. Yeah. I'm making you do a little bit of simple multivariable calculus, but I'm not going to make you actually do differential equations. But I think you should know what they are. That's what's going on. Letting you know what these things are, and you'll read about them. But I'm not going to be. They're kind of mostly a sideshow for the course. Okay.
Excellent. Gotcha.
We got 1 minute. Any other questions or comments here for the Labor Day weekend?
So, Dr. Usford's Noah. So should I just reach out? Should I just reach out to you with some like stuff that like you talked about earlier today? Okay,
well, I'll try to. Yeah, I might try to send you an email with a couple of things. A big thing you need to know. I'll show you how to take a determinant of a 2x2 matrix. That's something you're going to need, that definitely you need. So.
Sorry.
This PowerPoint, by the way, will be uploaded. Now, the one from last time was not. The one from last time was not.
You uploaded the one from last time.
I guess the last two lectures have been uploaded, but
the last PowerPoint's up. Yeah.
Yeah. Okay. So Noah, you can dig in, I guess, and should get the last PowerPoint. So if you can't find something, ask me a question. Feel free to send me emails and all that. Okay.
Okay. Is there anything from Thursday? Last Thursday?
Well, last Thursday I did a summary of the course, and a lot of it was sort of how we were operating. And so a lot of it had to do with exams. I mean, I kind of said this at the beginning. So you're gonna have 5 homeworks, and this is you can see this in the syllabus. There's 3 exams and 5 homeworks. And the homeworks you're allowed to work with each other. As I say, probably next time I'm going to send you the first homework problems. You're going to have a week or so to work on them. So you guys can cooperate on those. Exams you can't cooperate. It's going to be during a fixed time period. Okay. The other issue is about that book. I'm not sure what's going to happen. I have not put the book on reserve. Probably what will end up happening is that I may send you some simpler reading that will cover some parts of the book that something. So I'm not sure I can send you the book. Yeah, Cal.
I have the book on PDF, and I can send.
No. You have variant on PDF, right?
No, I have your book on PDF.
Oh, you have my book on PDF.
Yeah.
The second edition?
The second edition, yeah.
Oh my, well, he's got it. So, okay.
I can just send it to everyone.
Talk to Cal, he's got it. So it's available. Cal's real good here. He's got a bunch of stuff. So I will stop worrying about the book. So you can read the book itself and not have these. I might actually send you something else anyway, just with it. But you got the readings of the book are not until after the first exam. Okay. All right. Any other questions or loose ends for the moment here? So when you get back after Labor Day weekend, I'll send you out the first homework problems, but you'll have some time to work on it. Okay. Anything else? We're now overtime here, but we can run a little longer. Is that it? Anybody else got anything? Okay, everybody, stay well. Have a fun Labor Day weekend. All right, enjoy it. See you next Tuesday.
All right, see you.
I'm leaving now. Yep. Ending the meeting. Ping. End meeting. Ping.